Okay, so maybe I should begin.
If the recording is working, yeah?
Yes, I hope. Or I will re-record it. It's okay. So welcome everyone. My name is Quentin Lucas. So I'm a first-year PhD student at the ENSTA Bretagne in Brest, and I will present in this talk the objectives of my PhD, and I titled it Securing a High-Level Virtual Machine Through its ISA. So ISA is Instruction Set. And Faro as a case study is why I'm here presenting this to you. So I will go over a brief introduction just to give some security insights of why it should be important. And then I will apply that to the language virtual machines. So in this case, I will present some of well-known virtual machines and what vulnerabilities they can face. I'll present some JIT attacks and protections. So JIT is the just-in-time compiler. And then I'll present the idea that we had to secure a VM by following what has been done, the state of the art, but also our idea. We'll apply that. I'll present briefly the Pharo VM, but maybe you will correct me on what I say, and how we would like to apply the idea to the Pharo VM, and then the checkpoint, so where we are, what we did the last 2 weeks when I was here, and what's the roadmap for the next months or years. So first, I would just like to talk about code expansion. So basically, software applications are getting more and more dense and complex due to either the research for performance or security. So this is a good thing. Or the diversity of architectures, so either the number of processors that you have to run your application on, or the number of devices you have to support. So this is very true for drivers, for example. And to give an example, I just wanted to show the number of commits that are made to the Linux kernel per year. So to put in perspective, the Pharo project has 16,000 commits in total. So this is a third of what has been committed to the Linux kernel this year, for now. And to bring the scope a bit down, I would like to show the number of commits to V8. So V8 is the Google Chrome JavaScript engine. So that's embedded in all of our browsers. And this way here as well, we have 16,000, so the total number of Pharo commits that's in that will be reached in 2 years of commits of V8 VM. So this is just a small insight, but I will talk later on how this would apply to security reasons. So I will just talk about language virtual machines. So I added the keyword language as opposed to virtual machines such as VMware that would emulate your whole OS on top of your whole other OS on top of your computer. So here I'm talking about the runtime engine that's able to understand your source language and execute it. So all the different VMs usually have at least 3 of the components. So here on the left, so you'll have at compile time, so the bytecode compiler that will transform your source code into bytecodes. And then at runtime you'll have an interpreter that will be able to understand your bytecode and basically do a big switch on it and dispatch it to the actual function it has to do. And it works along with a garbage collector that will allocate and deallocate objects that are in use or not in use anymore. And the important piece is the fourth one, which is the Jit Compiler. That's when it sees at a given granularity, so it depends on the VM. It can be either a method, a basic block, or constants. it will recompile the bytecode down to machine code depending on the architecture it is deployed on, so it can boost performance. So I will use this feature more in the rest of the talk, but basically I just wanted to have on the left the different elements, and on the right the thing they will use in memory. So I put a stack here, but it can also be a register. For example, the Lua VM uses registers here to store their value directly, but the other ideas should be the same somewhere in memory. So VMs from a security point of view are present on all computer because they are embedded in web browsers, so often JavaScript VMs. And you can imagine that if there is a flaw in the VM, an attacker can simply pay a web server and send its malicious web page to the client or to its victim, and the victim will render the web page on his computer, and if there is a flaw in the VM, it can potentially execute arbitrary code on his machine. So some of the well-known web browsers VM are V8 for Google Chrome, SpiderMonkey for Firefox, and Chakra for Internet Explorer. And they are all JavaScript VM written in C++. And I added the Facebook hip hop VM, that's a PHP virtual machine, that's also written in C++. So the thing is, there is a heavy usage of memory unsafe, so C or C++, in virtual machines, because there are complex pieces of software that needs to perform both very high-level tasks and very low-level tasks, such as, for example, the Jit compilation that needs to produce machine code. So this leads to a list of vulnerabilities. So this is I just looked into the number of memory corruption vulnerabilities that can be found in Chrome per year. I'm using this graph because when I'll present the JIT attacks, often the attackers suppose that there is memory corruption vulnerability somewhere in the VM or somewhere in the application. So this is just to show that this is not particularly how would I say, a particularly bizarre hypothesis to make, because for now in 2021 we have found 3 vulnerabilities that are memory corruptions that can basically help you disrupt the execution flow or overwrite function pointer, for example. So I'll present some of the JIT attacks and protection that can be found in the literature. So the first ones will try to attack the JIT code, so the location in memory where you would have your machine code that is stored. So a basic idea of an attack can be the source code contains a call to a function that I call victim. When it's compiled down to bytecodes, you would have a bytecode that, for example, says call victim. And the attacker knows that this function will be called several times or will be Jit compiled at least somewhere in memory. And this memory will have all privilege, so read, write, execute. And the attacker can simply overwrite the machine code equivalent of the victim method in memory with his shellcode. So in the security domain, shellcode is the code that an attacker would like to execute on the victim machine. So this was possible in the very beginning, but is not possible anymore due to several protections, such as WXOR X. So this means that a memory page can either be writable or executable, but not both at the same time. You can prevent the execution of pieces of memory that you know that are data, such as the stack or heap, for example. And you've got a mechanism that's called address space layout randomization that will randomize the location in memory of objects, binaries, and libraries. So this all make the attacker have a hard time guessing where the JIT code is in memory and how to execute it. So there has been some ways to execute it anyway. So for example, this attack is called Jit Spraying. So basically you will have your source code with a variable that's a big XOR that's a big XOR of those constants. And the attacker will try to make this variable JITed, so recompiled in machine code. So for example, it would give move EAX, then the constant, and then XOR the other ones. And the idea is to disrupt the execution flow by 1 byte. So this means shifting the whole instruction flow, shifting the PC, so the program counter, by 1 byte. So that you have new instructions that will be revealed and executed. So this was found in 2010 in web browsers. So basically they would load a web page and it would launch a video, and then at some point in execution the web browser would crash and would launch the calculator application of your Windows computer. So there are some ways to protect yourself from this attack. First, I would like to say that to shift the execution flow here by 1 byte, this was performed on x86 architectures, because for example in ARM you'd have to be aligned by 8 bytes. So there are some ways, so you can blind the constants by XORing them at compilation with a random number, then re-XORing them at execution. So you would get the constant back, but the attacker won't see it in memory. You can obfuscate your code by adding some nope instructions in between your actual instructions, so the shift would be harder to make. The final attack that I'll present on the JIT code is called JIT ROP. So ROP is an acronym for return-oriented programming. So this means that the attacker will scan the memory where the JIT stores the machine code, and will look for gadgets. So gadget is a small sequence of instruction that's ending with a return, so ret. And for example, it would have a gadget for loading a value, gadget for pushing a value, any gadget that you would like. And he will then craft a chain of those different gadgets, and by doing so it can execute arbitrary code by saying first I would like to execute gadget 1, then gadget 2, then gadget 3, and by overwriting one function pointer to get back to the beginning of his rope chain. So this type of attack has been automated and is harder to protect from. You can protect from this attack by using, for example, control flow integrity, but this means that you have to generate the control flow graph of your program and then verify this graph over time. So it's often expensive in time and resources. You can also have non-executable memory, but this is not available on all architectures. So basically this is the go-to state-of-the-art attack if you would like to attack an ISA now or a Jit compiler, but it's very hard to craft and to conduct. So another idea is to directly attack the Jit IR here. So this was the case in 2017. So the idea, so the image is a bit dirty, but the idea is the step 4. So that was an attack conducted against V8. So when a function is declared as hot or in need to be recompiled down to machine code, the attacker will add crafted C++ objects in the IR chain, and the Jit compiler will compile the actual IR chain. So the genuine source code along with the attacker shellcode that's embedded in the IR. Another idea is to attack the bytecodes. So this can be done by, for example, overwriting a call function by pointing it to a system command, and the attacker can therefore launch any code that he wants on the victim machine. So those two attacks are made possible because the objects that I presented here in memory are often the result of C++ or C structures, and the attacker with some knowledge of VM and how it works can locate these objects in memory and add its own crafted objects or overwrite them directly. So protecting the JIT code is not sufficient. You will have to protect some other objects that the VM has to store in memory. So this brings the need for memory and process isolation. So this can go in 4 different levels. So the first one is memory page permissions. So you would have permissions of read, so R, write, or execute granted to a memory page. That's usually 4 kilobits of memory. But this is not sufficient, as we saw in the earlier attacks. So you can have added protection, such as memory protection keys. So this means that an application has to have a given key to have access to a memory page. And this can go even finer grain with domain keys, where you would have a per process isolation, and so an application can have access to a piece of a memory page along with a piece of another memory page, for example, but it can be smaller than a memory page and spread it along different memory pages. And the final idea would be to have a trusted execution environment. So this is usually a hardware enforced mechanism. That means that what's executed from within this environment cannot communicate with what's outside. So every vendor has some. So Intel has SGX, ARM has a trust zone, and RISC-V has a keystone. That's a proposition. So the solution to the bytecode attack that was presented earlier. So the same authors presented their protection. And basically the idea is to give a key to each of the important objects of a VM that are stored in memory. So what was here? So basically they would isolate all of the different objects here with a key, and the application has to get the key for a given permission. So here they gave a permission, so code can only be executed and not readable. The data can be read but is not executable or writable. So this gives a finer grain of control on what your VM does with objects stored in memory. And the other idea, so from the authors that presented the attack on the IR, is to use the trusted environments. So here they would completely isolate the IR and the Jit compiler itself, and they would add some other protection. So by doubly mapping the address in a way that's executable, a way that's writable, and they would give the writes only they really trust the application. So now I'll talk about what our idea would be when securing a VM. So the idea would be to defend the VM as an extension of its target ISA, and so that the mechanism of isolation that I just presented could be directly embedded in the target ISA. So for example, an instruction that's added to the machine code that you produce that would embed this isolation. So in order to do so, you need an ISA that's extensible. So I'll talk about RISC-V, which is an open source modular instruction set. So it has been created in 2017, and it is at the heart of open source processors. So what does that mean? This means that when you would like to have your application that targets RISC-V, it's split in several extensions. So you'd have a base integer instruction set for 32 bits, the same for 64 bits, and then you would have several extensions that each have a particular goal. So for example, M is integer multiplication, A is atomic instruction, etc. You have G, that's a shortcut for MAFD, so 32, 64, MAFD. And then you would have compressed instruction, and you have some extensions that are still in the draft status. So for example, you have the J extension that would be interesting for JITs or for garbage collectors. That's the extension for dynamic translated languages. So it's still an open extension, and anyone can propose a new instruction that would make sense in the field of dynamically translated languages. And you've got some other extensions as well. I didn't list them all, but you can look if you want to. So what does it mean to extend RISC-V? So you would have to design the new instructions with the available opcodes. You would have to add your instruction to the compiler so that it's emit your instruction at the right time, and then you'd have to extend a core. So you have several open source cores, so you can extend the core to make it understand your new instruction. Now if we want to secure our VM, as we said on the as I said earlier, we'll have to choose a VM that will port to RISC-V, and so that we can try to perform our experiments on. So I brought some examples here. So the two first ones are SOMs, so the Smalltalk Object Machine. They are toy examples that can execute basic Smalltalk code. CLOX is the result of Crafting Interpreter's book. So if you read the book and follow along, you will have a VM in C that's able to understand the LOX language. The issue with these two is that they don't have JIT and they don't have a RISC port. But basically the development cost would be low because they are quite simple. But again, the credibility would be low as well because they are not used in production anywhere at all. The next three I put are the exact opposite in the spectrum. So you'd have a JIT. Some of them have a RISC-V port, but the development cost to add something to it and to first understand it is very high, as I showed for the V8 with the number of commits it has. But again, the credibility would be high because every computer has V8 on it somewhere, except if you really don't have Chrome on your computer. But the credibility would be really high. And then we have some research VMs. So Maxine is in the Java VM. Lua JIT is a Lua VM that has a JIT. But both of them does not have a RISC-V port, or at least is in development. So the development cost would be high, and I stated that the development cost for the credibility, would be medium because they are less used than the three on top, but still more credible than toy examples. So I chose Pharo because of what has already been done to port the Pharo VM to other ISAs. So I'll just talk about that in the next slide. So why I chose Pharo? So what I just said is that the migration to other ISAs is either in process or completed, and there is a test harness that's available, and that's for the most part ISA agnostic. That will drastically reduce the development cost, and as I said, it's complex as it is in commercial use and more credible than the toy examples. So it's less used than V8 for sure, but it still mimics its architecture and can be credible. So I will present briefly the Pharo VM, even though I think that you know more than me about it, so feel free to correct me. If I take the figure I had earlier, so the bytecode compiler would be Opal, and the JIT compiler would be Cogit. With the JIT IR, that would be called Cog RTL. So this is just to put names on the things that are inside Pharo. So Pharo VM compilation is chain is as follows. So you'd have a VM that's written restricted Smalltalk, so slang. That would be transpiled to C. So you'd have your production VM in C, and then it will be compiled with GCC into an executable that you can deploy on the architecture that you target. So this means that in our case, if GCC knows how to produce a RISC-V executable, you would have a VM that is working on RISC-V, but you would still have to design the Jit compiler so that it is able to produce RISC-V machine code as well. Now if I look more into the Cogit Jit compiler, so it works in 3 main steps. So you'd have a bytecode scanning step, where the main goal is to extract metadata, such as the need for a frame. Then you would have a parsing phase, where you would generate the IR from the bytecode, so in Cog RTL. And the last phase is the actual code generation, so you would concretize your intermediate representation in machine code, and then you would get machine code. So what's interesting about these compilation steps is that all of the first blocks are ISA agnostic. So this means that this would be the same for ARM v8, for MIPS, or for RISC-V. So this is a lot of things that basically I don't have to do. And this is what was interesting. So another thing is that the VM there is already a test harness available. So a VM implementation for a new ISA runs through the 3 main phases of unit testing, integration testing, and end-to-end testing. But basically, applied to the VM, you would have to unit test the VM in the development environment, so within Pharo, using a simulator through FFI. And then you would simulate the full system using an architecture emulator such as QEMU, and execute the system on real hardware as the last step. So if I put this on a graph, I would have this with complexity and precision increasing as you increase your step, but the feedback speed and debuggability increasing the other way around. So this means that unit testing is the thing that has the less complexity, but the most feedback speed and debuggability. And in the end, you would have a more precision with hardware execution, but it's really a pain to have some feedback and to debug it correctly. So if we apply this to x86, we would have a unicorn that is a wrapper on top of QEMU that can give you functions to write or read a register, write and read arbitrary memory, or perform the execution step. Then you'd use QEMU itself, and then you would launch the VM on an x86 architecture, so probably your laptop, for example. If we look at what we need to do for RISC-V, so we need to look into the three different steps and how we can apply them to RISC-V. So the first one, the issue with Unicorn that was used for the other architectures is that it uses an old version of QEMU that doesn't have RISC-V in it. So we had to look for a simulator to perform the first step of the test harness. So there were 3 ways of defining which simulator to use. The first one is Spike, which is the simulator used by the RISC-V community. But the issue with Spike is that it doesn't have a shared library, so it's just an executable that you can feed RISC-V binary and that it would present you the result of what you did. So the first option was to extract a shared library from the Spike simulator. Another possibility is to extend Unicorn to port it to a newest QEMU that can support RISC-V. And the last main idea was to craft a RISC-V simulator ourselves from within Pharo. And on the right you can see, so the cost is the development and maintainability cost. So for Spike, development cost is kind of low, so we have to find how we can expose some of the Spike inner API to our Pharo FFI. But it can be a pain to maintain on the long run. On the other hand, Unicorn, if we port the Unicorn to the newest QEMU that supports RISC-V, the development cost and maintainability is very high because you'd have to basically rewrite Unicorn. But you would get long run viability that's very high as well, because it could be maintained by a community. And on the other hand, the handcrafted solution is medium in terms of cost, because this means that you still have to write all the simulator by hand, but it also means that you don't really trust the official simulator, so it still has a low viability. So this is for the simulator part. So we chose to extract a shared library from Spike because this is what looked like the lowest development cost and that still uses the tool that has been developed by the RISC-V community. For the full system simulation, so QEMU supports the RISC-V architecture since 2016, so it's cool. And for the full system hardware execution, there are two possibilities. So either we use a solution that's written in hardware description language. So this is a low-level programming language that can help you program programmable boards. So this is useful in the sense that we'll have to do this at one point if we want to extend the core and port it to an FPGA. So this is a programmable board. So the example is Ariane, or the CVA6 core, which is an open source core and that is available for anyone to use, and it's supposed to be able to run a Linux distribution. And another way is to use a RISC-V processor that's directly built and that is available, but that cannot be extended to use our custom instruction in the end. So now I'll go over the checkpoints of where we are, what did we do in the 2 weeks that I were in Lille, and what are the next steps. So what did we do in the 2 weeks? We extracted a shared library from the Spike simulator. So with a custom API that we can call from Pharo. I wrote forked, but it's rather a copy of ARM v8 Jit Compiler, and we redefine some simple concretization. So the passage from IR to machine code, so it is correct with RISC-V instructions. And in the end, we got the first green test from Pharo on very simple Pharo bytecode that is Jit Compile. So what are the next steps? So in the engineering world, we'll still have to extend the Jit Compiler to cover all of the existing tests that are available in Pharo. And then we'll have to perform the two others test steps. So the full system simulation and the real hardware execution. And then more on a research mindset, we'll have to define applications and scenarios that make sense to perform an attack on. then we have to actually perform an attack and define countermeasures with a given granularity. So either the memory protection keys that I talked about, either enclaves with hardware enforced environments, and see how it can be applied to JIT, or adding an instruction to the instruction set that can do what I just said, but directly from within the Jit compiler code emission. So in conclusion, on the security side, memory isolation seems to be a security improvement in virtual machines that can come as not low cost, but as hardware enforced. So you can have a VM that's secure by construction. For the VM choice, we choose Faro as a compromise between development cost in terms of porting the VM to RISC-V, since it already has a test harness and a Jit compiler, and credibility. And for the experiments, the RISC-V port will allow us to conduct some security experiments in terms of how we will choose the countermeasures, at which granularity. So as I explained, the memory protection keys, trusted environments, or embedding the two in an instruction. So there are still many open questions, so both on the software side, so what does an application need to protect, what is an attack scenario for Jit compiler. On the hardware side would be how to protect the components, so at which granularity, and what does a new instruction for the Jit compiler would do. And more on the meta, so to defend the credibility side, is how we can define links with other VMs, how the Pharo VM is similar to other VMs, which is mostly similar by construction, so the different so Jit compiler, bytecode compiler, etc. are present in all other VMs. So how we can define links with other VMs to create guidelines on security, or why not a proposal in the J extension draft in the end. So this concludes my presentation, and if you have any questions, I'll be happy to try to answer them.
So I have, but I don't know if it's really a question, but at some point you showed an histogram of the. You don't have to go back there. At some point you showed an histogram of the memory corruption errors. Attacks that were corrected in I think it was V8.
Yes.
My question is: so you said you're looking for scenarios. Isn't there something already in literature, or if not in literature, online from these tons of VMs that do JITting, in which you can take inspiration for this attacking scenario?
Yes, so there are a lot, but the thing is we still have to be credible against them, so we have to implement the defenses that they put, so that on our side we are attacking, so that we don't redo the for example, the very first attack where we simply overwrite a piece of code that was very vulnerable. So we would have to have some defenses that are available on the VM or somewhere, which is what I call the attack scenario. Is more the definition of the defenses that we have, the definition of what the attacker should have. That's not too that's a correct hypothesis. So for example, the fact that he knows that there is a memory corruption or memory disclosure vulnerability somewhere in the system, and this is what should define the attacker and attack scenario.
Okay, you were breaking a bit, but I think I understood.
Okay. Yeah, what I was saying was just that attack scenario is more a definition of defenses and the attacker resources. And yes, it should be already defined in the literature, but it still has to be clarified for us.
Okay.
Kantan, you missed to say something very important that you did the couple of weeks here. That you started having a debugger, a machine debugger.
Yes, that's true.
It's very important
Yes,
because
that's true.
all the tools that we already have.
Yes, that's true. Now we have a machine debugger for RISC-V. So this is, wait, we posted it somewhere, but it's basically a reuse of what Gish and Pablo did for the other instruction sets and applied to RISC-V. So we use the LLVM disassembler to see what's happening with our RISC-V instructions.
And we are missing a demo. You should show the two test turning green.
Wait, I have to see if they are still turning green.
But like that, like a crappy demo. Look, it turns green.
Let's hope they still turn green. So those are the simplest from the so VM simple stack based bytecode. So there are single bytecode. So this one push constant false. So it's just push.
Yes, maybe there you can put a halt and show in the debugger. That is the most, I think.
Yes. Okay. I should just. So yes. So this is our how do we call it? Machine debugger with the different instructions that are RISC-V instructions, and yeah, we can just set instruction pointer here. Oh wait, I have to, yeah, okay. So the PC, so basically we redefine the different registers that need to be shown in the machine debugger and the way to disassemble the actual instructions. So next we can just step and see, yeah, how the stack moves, and I don't really know. So this was the result of 2 weeks, basically. So now there are still lots of tests that need to be compliant. Okay, so I don't know if you had any more questions. I tried not to be too specific with JIT attacks and defenses. I hope that you still get what are the main ideas.
When you have an attack, show us. That's all.
Show us.
I want to see one real attack, but on Pharo. No, I'm telling you.
Okay. Yes. Yes, this will be the goal, I think, right after, or maybe in parallel. Yeah, the two main goals are to have the Pharo VM working on RISC-V, and then an attack scenario that we can conduct on the Pharo base RISC-V set, and then see how, with our extension or our protection, we could mitigate this attack. Okay, so this should be it.